order to really understand ultrasound, you have to know something about wave physics. And this lecture will give you enough to really understand how to do ultrasound, what the basics are, and I'll probably go into a little bit more detail than you really want, but let's see how we do. So to understand what ultrasound is, you first need to understand what sound is. And sound is a type of wave. I talk about the history of ultrasound a little bit more in another lecture, but these early adopters of ultrasound, bats, whales, and eventually boats and submarines, really brought about the creation of our diagnostic ultrasound. So Lazzaro Spallanzani, he was the physiologist to discover that bats use ultrasound to locate things in their environment, and that led John D. Culloden to discover that sound can be transmitted through water. He used bells in Lake Geneva. And then Paul Langevin discovered, or was inspired rather, by the Titanic crash into a glacier to create the first transducer that allowed boats and then later submarines in World War I to use sonar to discover other large glaciers and submarines around them. So what is sound? Sound is just a wave, and there are two major types of waves. The first type is electromagnetic waves, and those are, includes light, X-ray, infrared, radio. Those are all things you could blast into space if you wanted to, because they travel within a vacuum. But there's no point in trying to yell into space if a UFO is coming at you, because sound does not travel through a vacuum. There's two types of mechanical waves. One is longitudinal, and that's what sound waves are. I'm going to talk a lot more about that. The other types of waves are transverse waves, and those are kind of the traditional ones we think about. Typically water waves, you think about waves in the ocean, that's a transverse wave. Also earthquakes is another type of transverse wave. Let's briefly talk about transverse waves just because we're going to talk mostly about longitudinal waves, which are sound waves. First, the definition of a wave is energy moving in space. And a transverse wave is the one you see at the top of this image here. It moves up and down just like the waves of an ocean, and the material travels 90 degrees perpendicular from the direction of the wave. So the wave is, in this graphic, is moving left to right. But if you were, say, floating on your back in the ocean, you would actually be moving up and down on the wave. You would not move left to right. And that is different from a longitudinal wave, where you have areas of compression and expansion, or compression and rarefication, that might oscillate you back and forth. Now, sound waves are longitudinal mechanical waves, not just longitudinal waves. So the wave part means it's energy moving in space. The mechanical part means that it requires material for this to happen. And then the longitudinal part of the definition is that material travels in parallel or in the same direction as the wave. So that is very different than a transverse wave. So again, sound waves are mechanical longitudinal waves, and they have to travel through a medium. There has to be material present, and that's why these cannot travel through a vacuum. Now, they can travel through air, water, tissue, solids, and they travel at different velocities through different mediums. Look at this graphic here, and it just helps illustrate that even when we draw a wave out pictorially, this sort of blue squiggly line that's going up and down on the depth curve, that's to represent what the amplitude, what the frequency of the wave is, but that's not really what a wave looks like, and it can be confusing. So it looks like we're almost drawing a transverse wave, but we're actually talking about a longitudinal wave. And so that's why this portion on the bottom, rarefication and compression, is listed to show you we're talking about a longitudinal wave. And compression is when the tissue is being compressed by the wave, put very close together. Then rarefication is a decompressive force. That's when it kind of separates the tissue. And that's what happens when you shoot a longitudinal wave, because it's just pressure. You add pressure to something and it swings one way and then it swings back. So you have these sort of areas of compression and refraction. So rather than waves going up and down the ocean, it's kind of like you have waves going left and right, or the same direction of the pressure wave you're pushing through tissue. So let's try to explain that a little bit more. So sound and ultrasound is a longitudinal mechanical wave. and it transmits through a medium by locally displacing particles within that medium. So say your medium is water or tissue, you put the ultrasound probe on it, and it's literally pushing waves, pressure waves, through that tissue, like coming straight out of the probe, straight out of the transducer, and it's moving those particles in that same direction of the wave, and they're oscillating back and forth, areas of compression and rarefication back and forth. And that's what the wave is, and that's how you get some information coming back to you. So if that red dot is the particle on our blue arrow, the ultrasound pressure wave makes it go back and forth, back and forth. And the frequency in which the particle is made to oscillate back and forth, that's what defines something as ultrasound. So sound is defined as being in the audible range. So it's a longitudinal mechanical wave that we can hear with our ears. And if we oscillate the particles to a higher frequency above our audible range, so usually more than 20,000 hertz or 20 megahertz, then that is a ultrasound wave. So it's just above the audible range. That's what ultrasound is. So let's better define frequency. We just said that the frequency needs to be really high to be ultrasound, more than 20,000 hertz generally. Just look at this picture on the top right here. And this pictorially kind of shows you what low, medium, and high frequency would look like. Low frequency on the top, there's not that many ups and downs of that curve in that given period of time, whereas the medium one, there's more, and then the high frequency at the bottom, there's more sort of up and downs of that curve over that same period of time. And that's what frequency is. So frequency is defined as the crests of a wave that move past a given point in a given unit of time. And we describe it in hertz, which is cycles over a second. It does not typically change through mediums. The velocity will change through mediums, but the frequency will not. The next thing to define is wavelength, or also known as period. So wavelength is the distance between successive crests of a wave, especially points in a wave, in a sound wave or electromagnetic wave. So the wavelength really depends on the frequency and the medium in which the sound wave is being propagated. Higher frequency, meaning there's more of these waves going up and down, naturally the wavelength will decrease in size. If you look at this picture on the bottom, you can see that if you were to stretch that wave out, the wavelength would have to get bigger, and if you'd have to push that wave in, if you compress it with your hands on either side, the wavelength would decrease and the frequency would increase. So it's inversely proportional to frequency. Wavelength equals 1 over the frequency. Next thing to define is velocity, and that's distance over time, so how fast something is propagating through a medium, essentially. And the speed in which sound propagates through a medium is defined as velocity, and it's inversely related to the density and directly related to the stiffness of the medium. So that means that if it's a very stiff substance, that the velocity of the sound wave or mechanical wave will go very quickly. And then the opposite is true as far as density. So if you wanted a wave with a high velocity, you would choose a very stiff, not as dense tissue. You can see that most of the tissues in the body, based on this chart here, travel about the same speed, around 1,450 meters per second or a little bit more, except for bone, which is a very stiff and dense tissue. If you know something about ultrasound, you know that most of those waves get reflected off the bone, and ultrasound is not the main way we want to evaluate bone for that reason. Now that brings up another acoustic principle, which is impedance, which we'll talk about a little bit later. Now there is something called the wave equation, which you should know about since we're talking about waves here, and that's wavelength equals velocity over frequency. So if you were given a test question and they gave you the velocity and the frequency, you can make them the same type of units and then figure out what the wavelength is or figure out what the frequency is. I think you could certainly work that equation out on a test question. The next definition to get through is amplitude. So amplitude is this last arrow here the chart. That is kind of the size of the wave or how tall it is on the graph. And it's also referred to as the magnitude of the pressure change, and also is kind of correlated with the intensity of the wave. And that's how you should sort of think about it. If there's a very small amplitude, it's not a very intense wave. It's probably not going to be very powerful. But if it has a large amplitude, it's very intense and it can become very powerful. Now there's another process to understand here, that power is the squared unit of amplitude, and power is also a function of how focused the wave is. So taking the sun and the magnifying glass as an example, if you were to take ultrasound waves or sun waves, electromagnetic waves in this case, and then focus them on a single point, you would take that intense wave and then make it much more powerful on a single point, and then that can light a piece of paper on fire. In the case of ultrasound, that can be targeted to lyse tumors and things like that. So the units for amplitude are watts. And we try to adjust this in ultrasound. There's a lot of safety check marks built into the machine to make sure that the intensity and the power is not high enough to cause harm on your diagnostic ultrasound. Now to review, there's a couple take-home points as far as diagnostic ultrasound. Just remember that long wavelengths equals low frequency and short wavelengths equals high frequency waves. And in long wavelengths or low frequency waves or transducers that produce those waves, those travel deep into tissue, but they'll provide very poor image resolution. Whereas short wavelengths or high frequency waves or transducers will provide really good resolution, high resolution images, but they won't penetrate very far into tissue, so you'll use those for very superficial things. A couple other chief principles about ultrasound that you got to know. Attenuation. There's also amplification. We're not going to talk too much about that because that often doesn't happen with ultrasound, at least diagnostic ultrasound. But attenuation is a measure of the rate in which the intensity diminishes as that ultrasound wave penetrates through tissue. And this happens through any tissue in any diagnostic ultrasound. That's why you only want to use the depth that you need, because that quality of the image decreases as it goes deep into the tissue, because some of those waves get scattered, some get refracted, some disappear and turn into heat, and then some get reflected. And so each tissue has its own sort of attenuation scale, and the units are measured in negative decibels. And you can use the decibels to figure out what the amplitude is doing on your wave. So if you have -3 decibels, that equals to half the amplitude, or subtracting half the amplitude from your wave. The other thing to note about the amplitude and the attenuation is that it's directly proportional to the frequency and the distance, and that's why those high frequency probes that we use for like vascular studies or to put in lines for procedures, that's why they're only used for superficial tissue, because those are high frequency, higher amplitude waves. But the attenuation is directly proportional to the frequency and the distance. So the more distance you have and the higher frequency of the ultrasound wave that you use, the higher the attenuation will be. And that's why those high frequency transducers do not penetrate into tissue very well. Now I want to summarize and talk about a few acoustic variables before we move on to another topic. So pressure, now remember these are longitudinal mechanical, or also called pressure waves. So the amount of pressure you exert on tissue will make a difference of how the wave reacts to that tissue, the quality of the image you're seeing on the machine. And so you start with that pressure wave, and then you push that pressure wave, whatever wave that you're using, into the tissue. And the tissue has a few dimensions to it. We call that tissue elasticity. And that's broken up into two separate categories, density and stiffness. So each tissue has a specific density and each tissue has a specific stiffness. And the stiffness is going to allow that wave to propagate really well, whereas the density will reflect those ultrasound waves and not allow it to move along very well. The temperature may increase the velocity in which these particles go back and forth, and then the distance of the particles, or the wavelength, will also change the way that the wave reacts with tissue and what you will be seeing on the machine. Now, impedance is the acoustic resistance through the medium. So we talked about attenuation, and that just always happens no matter what. But impedance is actually what allows us to differentiate tissue. It's what allows us to actually see images and visualize anatomy. So it's an important concept to understand. So it's a characteristic of the medium, and it cannot be changed. It's in units or rails, and it's the density times the velocity. And each tissue has its own. And when you put two different tissues next to each other, they have two different impedances. And the ultrasound machine can understand that two different things are going on because the ultrasound waves are hitting those two different tissues, and they're bouncing back at different amounts. And the ultrasound machine interprets that and can show that on the screen. So by having tissues with different impedance, by having tissues with surfaces that are rubbing against each other, that creates enough differences in how the ultrasound waves bounce back and react that you can see differentiation on the screen. So another way to put that is how I did in the bottom here, that the impedances between tissues, it changes the ratio of the reflected and transferred waves, and that's the whole reason we can see differences of tissue on the screen. One other thing to mention that you may not ever hear again, but it could be a topic or a phrase that is out there in the literature, or if you ever go, study for RDMS or anything like that, is the half value layer thickness. So the half value layer thickness is the thickness of the tissue required to reduce the sound beam by 1/2, and that's -3 decibels. Remember, that was 0.5 or a half of the amplitude when we were talking about attenuation. So a half value layer thickness is equal to 3 over the attenuation coefficient, and the attenuation coefficient is the frequency over 2 of whatever frequency you're using. So this is just something you might have to use in an equation, usually on a test or something. Other than that, you don't necessarily have to remember this half value layer thickness. And last for this lecture, we'll just briefly talk about refraction, reflection, scatter, and absorption. These are all things that happen all the time when you use ultrasound. And all these put together are what creates the image that you're looking at on the screen. So you have to know about all of these. And then you have to know about all of these to understand what the artifacts are so you can interpret the image. And that's what we're mostly going to talk about on the next lecture. So first, refraction. We have two tissues that are next to each other. That sound beam or light beam, whatever wave you're talking about, the angle and the speed or velocity will change. So if you have air on water, or air on tissue, or tissue on water, all those sound beams moving through that tissue, and then once they hit the water or blood, they will get refracted and their angle will change. So that there is a distortion happening whenever you're visualizing tissue and fluids and the interfaces between them. And so you have to understand that that can happen. But at the same time, reflection's happening. So whenever you point the ultrasound transducer on anything, a bunch of those waves are coming right back to the transducer, and those are the ones that get interpreted or put onto the screen so you can interpret them. So that's how you get your image, but not all of the waves are coming back. Some of them are being refracted and you never see them again. Some of them are being absorbed, and that's when it hits tissue, it gets turned into heat. It's a byproduct of ultrasound. It just happens, and you'll never see those waves again. So not all of them are getting reflected, so you have to appreciate that. And then scatter happens too. This happens a lot with air, and it just moves the ultrasound waves all over the place. They don't get back to the transducer, so you're not going to be able to interpret those waves. You're not going to see them back. And that's just a natural thing that can happen with certain types of mediums, and you have to understand when that can occur so you can interpret your image properly.